Hi everyone, welcome to week 7 of our biochemistry weekly reviews. I know you guys have your exam tomorrow, so we're going to review a little bit at the end, and then we're also going to have a little bit of time for questions about anything in this unit. But very briefly, I just want to go over some of the things we were talking about this week. So the first question we have here, and this is more from last week when we were talking about inhibitors, is does CHEM ever change? So this is one of those topics that I think a lot of people say yes, it obviously does, because when you're dealing with, for example, a competitive inhibitor, you see that CHEM increases because the affinity of the enzyme for the substrate goes down. And the reality is that while CHEM seems to change, this is a really important concept that a lot of people get confused, it isn't actually changing. And so what we see is, oh, sorry about that. I'm not sure why my mouse isn't working. So what we see, there we go, is rather than an actual change in CHEM, we see a change in what's called the apparent CHEM. So I'd like to talk a little bit about this. So CHEM is basically intrinsic to the enzyme, okay? And what that means is that for enzyme E to substrate A, CHEM is fixed. Okay? Because the enzyme always has the same affinity for this substrate A, because the active site is the same and the substrate's shape and structure is always the same. And so CHEM is a fixed value. What we see with competitive, non-competitive, and uncompetitive inhibitors is that CHEM seems to change because of the disruption caused by the inhibitor, or in case of non-competitive, CHEM doesn't change, but something changes. And it changes by this factor usually. So we see that in competitive and in uncompetitive, especially. We see it in the Vmax for uncompetitive and for non-competitive. But for mixed inhibitors, we see this other weird thing called alpha. Okay? And alpha is pretty much the factor by which we need to scale up our substrate concentration in order to make up for the presence of the inhibitor, if that makes sense. Okay? So the real key here is just keeping in mind K itself is not changing. Okay? All right. So now let's talk about some of the stuff that that your professors talked about this week. Single displacement reactions and double displacement reactions are two of the biggest ones. So these are two examples of a single displacement reaction. So just a little bit of brief notation stuff to make sure. E is going to be our enzyme in every case. A and B are our two substrates, okay? So with these reactions that we're talking about, they're bi-substrate reactions. So this first one that we see here is called random. And the reason that it's called a random single displacement reaction, well, let's talk about single displacement first. If we notice in both of these, this is the same. And actually, let me highlight it. I think that's, yeah. This is the same across both of them. This is what makes it a single displacement reaction, is the fact that we're creating product only once, okay? However, this is called random and this is called ordered because of the way that the substrates bind to the enzyme. So in the case of the random, A or B can bind to the enzyme alone to create either AE or EB. And then if we have EB, A can be added to this reaction. If we have AE, B can be added to this reaction to create AEB. And then the reaction can occur, that displacement can occur and give us PEQ, where P and Q are our two products. And in the same way that A and B can be added in any order, P and Q can be, oh, I'm sorry, this one should be Q. P and Q can be released in any order, okay? And so that's what's called a random single displacement reaction. For double displacement, or I'm sorry, for single displacement, for ordered, it's a little bit different. In this case, what we see is you have to add A to just the enzyme. then to the AE complex, we can add B. That's when we get this beautiful displacement reaction happen. And then again, Q has to leave, and then P has to leave in that order. Okay? So the reason it's called ordered is because they have to bind and be released from the enzyme in a specific order. And a lot of people will be like, well, how does that work? So one of the ways that we sometimes talk about these reactions, and this is more a double displacement concept, is the enzyme is almost changing conformation to allow for that to happen. And again, that's a double displacement thing more than a single displacement, but the idea works the same way, that by binding to A, my enzyme is now able to bind to B, okay? So instead of changing shape, maybe it's that our enzyme looks like this, A looks like this, and B is this. And A is okay with binding to just the enzyme, but B needs to bind on both sides. So it has to have A present. Something like that is the reason that it has to be ordered, whereas random could just be, let's see if I can draw this. Something like that, where A can bind here and B can bind here. Does that make sense? Okay, terrific. All right, so let's talk about this in terms of the graph. And these graphs are fairly commonly seen on exams. I don't want to say this one in particular, but either the single or the double displacement one, and you need to know which one is which. So this, as it says right here, resembles what a non-competitive inhibitor would look like. So as we increase the concentration of B, from B to 2B, and then even to 3B, we see our y-intercept decrease. Our y-intercept decreasing, well, our y-intercept is 1 over V, which means that V increases. Okay, let's pause real quick. Does that make sense? Yeah, sense, right? Because as you increase your concentration, your rate speeds up. Now, is this V max? Not quite, because it's affected by two different reactions. It's kind of the speed of the overall reaction, like the overall both reactions happening. Okay. All right. What's happening to our K, and for simplicity, they call it KSA. So K of the substrate, and specifically of substrate A. Okay. It's decreasing. So this is B, this is 2B, and then this is 3B. It's decreasing. Why is it decreasing? Okay. So the basic reason why it's decreasing is, so x-intercept is decreased, but it's negative, right? So really the value is increasing. If the value is increasing and the value is the 1 over k, then that means that k is decreasing. Does that make sense to everyone? Because I feel like the negative kind of throws things off. Are we okay with k decreasing? Okay, awesome. So if k is decreasing, then what that tells us is that the affinity is increasing. And again, let's ask, does that make sense? I'd say it does, right? If k continues, or if I keep adding b, then let's talk about right here. If b keeps going up, then my affinity to get to AEB is going to keep increasing as well. And likewise, if b keeps going up here in this top one, then what we're going to see is more formation of EB, more formation of EB, excuse me, is going to increase the equilibrium concentration of AEB, right? And so that's why we see affinity increasing and V increasing as well as we increase the concentration of substrate B. Okay. So now let's talk about double displacement reactions. And double displacement don't really have single and ordered, because the key to double displacement reactions is we see two reaction equilibria. Okay, so we see AE to PE prime and E prime B to EQ. So let's talk about this one a little bit, because this one can be pretty confusing as well. So what's really happening in this half is that A is being converted to P. But when that happens, the enzyme E is changing somehow, okay? And then this changed enzyme is now able to bind to B and help it react and become Q, which brings it back to its original conformation. So a great example of this would be something like, excuse me, a kinase or a phosphatase, right? If they're adding a phosphate group and they're not using ATP, then maybe it's enzyme with a phosphate, and it's transferring this phosphate to A. And this will be PO4, I guess. I'll label it just so we don't get it confused with P for product. It's being transferred to A, which converts it to P, which is just going to be A plus PO4. And then in doing so, this enzyme is now E prime since it no longer has a phosphate group. And then B, let's say B synthesizing Q is going to transfer a phosphate group back to the enzyme, okay? So while this order kind of helps, I like this kind of hexagon diagram because I think it's a lot more intuitive, because you can go in any direction, but the binding is specific. So if you have your enzyme, you can either bind, or you're going to bind to A. Your enzyme binding to A is going to convert to P, and then P is going to leave, and you're going to be left with E prime. E prime binds to B, converts. This is a mistake. This should be a EQ, I think. Yeah, this should be EQ. There's a mistake in this diagram. There we go. So E prime B converts to EQ, and then Q can leave, and you're back to E. You can also go backwards. E can bind to Q, convert to E prime B, and so on. Okay? And then this kind of, this part on the right kind of shows why it's called a ping-pong reaction sometimes, because you can go from here to here, from here to there, and so on and so forth. So it resembles ping pong, and then it goes back and forth a little bit, okay? And actually, before we go to the graph, are we okay with kind of that idea of double displacement reactions? All right, awesome. So let's talk about the graph here. So once again, it's the same thing that we're looking at in that we go B to 2B to 3B. But this one, rather than resembling a non-competitive inhibitor, resembles an uncompetitive inhibitor. So once again, we see V decreasing. And once again, we see K decrease. We see the y-intercept decreasing, which means V is increasing. And we see K increasing to the negative side, which means that K is decreasing. But the graphs themselves are very different, because in this case, the slope is very variable. However, in this case, the slope is a constant. Okay, and the reason that it's a constant is that as I increase my concentration of B, my rate and affinity both increase, and I should say Km of A, both increase proportionally, because as I increase B, here we go, as this increases, Le Chatelier's drives this equation all the way around, and so the proportion by which I increase B increases by my speed by that same amount, but it also increases the rate at which E can bind to A because of that change in conformation, okay? So because of that, the slope is a constant, okay? Does that make sense to everyone? And I want to pause because this can kind of be confusing with the graph. Awesome. So the next question that you guys can kind of see a little bit of is, how do exchange reactions help us tell whether our reaction is single displacement or double displacement? Okay, so let's talk about what an exchange reaction is firstly. So you'll most likely have seen them in your notes as it helps you tell them apart. But what an exchange reaction can do for us, and I'm going to use the same notation that we've been using above with A and B, is if I have A plus B, I should say A plus B, and you've got an enzyme and it goes to P plus Q. That's all we know. We don't know whether this is single displacement or double displacement. So what I can do is just add A. okay? If I only add A, let's go back up to these graphs up here. Oh, let me zoom out. Or let's go back up to this diagram. If I only add A, will I see a reaction if I have a single displacement? What do you guys think? So if I add A up here, then I stop right here. I have AE. So the question was, if I only add A to a single displacement, like to this mechanism, that's a single displacement mechanism, will I be able to form product? Okay? And the answer to that is no. And the reason is, if I don't have B, I cannot get to this part because I need B for it. So my reaction is going to stop at AE. Or I should say, my enzyme is going to bind to A and then not be able to do anything else. Because the key to a single displacement reaction is you have both bound and then they both react. Likewise, in this ordered reaction that we see down here, A binds to E and stops. We cannot keep going because B is not present. Okay, does that make sense? So exactly. So for random and for ordered, we need B to react because the key to a single displacement reaction is the highlighted equilibrium in the middle. You have A plus B both bound to the enzyme, and it results in both products being formed. Okay? All right. So one of the other ways that people use exchange reactions, and this is a lot more of the like real life chemistry stuff, is they'll tag B with something that's fluorescent or something like that, and so it'll tell you is B bound to the enzyme at the same time as A or something like that, or it'll show you a little bit more. But this is a more simple example that I think really illustrates the point of an exchange reaction. Okay, so do enzymes bind substrates or transition states more tightly? So this comes down to transition states. Yeah, someone beat me to it. You're exactly right. So this is why enzymes work, and that's a lot of what this part of the chapter is about. Is why do enzymes actually make product happen? And it's because when we look at our activation energy, we keep hearing it lowers the activation energy, and that's nice and all. But what does it actually mean for us? It means that this up here is our transition state, and that's usually assembled with this kind of, I call it a train track. I don't know what the official name is. So our train track thing, our transition state, if we bind to it favorably, then it makes our reactant want to become it more spontaneously. I shouldn't say more spontaneously, more quickly and more easily. Okay? So this is also, and I talk about this, in two questions. This is why transition state analogs work, because transition state analogs, for those of you who haven't had a chance to study it yet, they're basically competitive inhibitors, except instead of resembling R, they resemble our transition state. Okay? And so because it binds more favorably to the transition state, it stabilizes it a lot and lets that reaction go to completion by making the formation of the transition state more favorable. Okay, does that make sense to everyone? Okay, all right, awesome. Actually, let me slide this over so you guys can see the numbers for if we want to refer back. I forgot about that. Okay, so number 6, does the lock and key hypothesis or induced fit hypothesis favor the formation of the transition state? So, someone beat me to it. Induced fit, yeah, you guys are exactly right. So just a quick recap, the lock and key hypothesis basically says, my enzyme looks like this, my substrate looks like this. They bind and they're happy. The induced fit is something kind of similar. It basically says, if this is my enzyme and this is my substrate, my enzyme can change, I don't want to say change conformation because that brings back the idea of the E prime, but it can fit this substrate in it because of the active site kind of being induced to fit in there, okay? And so the reason that this favors the formation of the transition state, actually, let's ask you guys. You guys were very confident that it's induced fit. Why does that favor the transition state? What do you guys think? I mean, you're right. I just want to hear a little bit more. Something to do with stability? Yeah. Well, yeah. So the induced fit model, basically what it says is that, how do I word this? The induced fit model gives an accurate description of specificity. Okay, so it says this enzyme is specific for this substrate, and they can distort, both of them can be distorted into a transition state conformation. So for example, when my substrate initially fits, it looks kind of, it struggles to fit in here, right? It's going to kind of do that. And so what's going to happen is when the enzyme, since the enzyme is able to distort itself just a little bit to fit in there, it favors the formation of the transition state because it includes the idea of specificity actually working. Okay? I know it's not the best example, or I know it's not the best explanation because it is a little bit of a really weird explanation, but the most important part here is understanding that induced fit favors the formation of the transition state. And remember, based on number 5, the formation of the transition state is, or I should say, the transition state being more tightly bound to the enzyme than the substrate is why enzymes are actually able to speed up reactions. And so that's how we confirmed that the induced, or that's how we kind of strayed from the lock and key hypothesis to the induced fit hypothesis. Okay? All right, so the next question that you guys can see up there is, why are transition state analogs, or TSAs, more effective than competitive inhibitors? This is one that we've kind of talked about before, so I'd like to hear a little bit from you guys. What do you guys think? It resembles structure. It mimics the transition state structure. Yeah, those are both really great explanations. So basically, if as we established in number 5, enzymes bind transition states more favorably than substrates. Well, competitive inhibitors resemble substrates, but TSAs resemble the transition state. So the thing that resembles the transition state is going to bind more tightly than the thing that resembles a substrate. Okay, so exactly like you guys said, it's able to mimic the transition state structurally, it resembles the structure, all these things. You guys are exactly right. Okay, and that's kind of as far as I dove into the specific inhibitors they talk about. So in your notes, you professors very likely talk about irreversible inhibitors. They talk about specific ones such as sulfa drugs, Viagra, etc. I strayed away from talking about those because some professors want you to know all of it very well. Some professors don't really care to talk about it much. And so I didn't want to include a ton of unnecessary information. I didn't want to include a little bit and say that's as much as I think you need to know. So I'm going to leave the specific inhibitors as a do what your professor has told you. Okay? All right. So now shifting gears, the second thing we talk about in this chapter is, after we've talked about the idea of enzyme binding, we talk about mechanisms of enzyme catalysis. In other words, how does my enzyme actually do what it's supposed to do? Okay? So does anyone, and I can make a poll for this, but there's only a few of you, so I'm going to ask, does anyone know which of the following is not one of the mechanisms of catalysis? Yeah, see, you guys are exactly right. So very briefly, we're going to talk about this. Catalysis by proximity is the idea that it's something called a near attack complex. Okay, so when atoms are within a certain distance of each other and at a certain angle, which I don't think you need to know all the details of, it allows for whatever reaction wants to happen. So, and this might not be an actual reaction. This could be just them being near each other allows allows a quote-unquote bond to be in the transition state to stabilize whatever needs to be stabilized. Okay, I think the example in your slides is going to be something like a carbonyl. As we know, this carbon right here is electrophilic and partially positive. So if we have something that's like an O minus, it's able to have this this interaction to stabilize this carbon, and that might allow some reaction to happen. So that's catalysis by proximity. Covalent catalysis is exactly like it sounds. It's the formation of a covalent bond. Okay. Now I want to point out it's a very, very temporary covalent bond and is always broken because we have to regenerate the enzyme at the end, because otherwise it wouldn't be an enzyme. So it usually happens with a nucleophilic attack or some prosthetic group, and it tends to facilitate an electron transfer. Okay. So the whole point of most covalent catalyses is quick attack for quick nucleophilic attack. Okay, we've caused some change in conformation. Great, now we can go ahead and let the next reaction happen, and then my nucleophilic amino acid in my active site is going to be regenerated. Okay, that's covalent. General acid-base catalysis is one that I'm sure you guys vaguely remember from organic chemistry. Usually you'll see just H plus or OH minus or something, and it tends to basically cause H plus transfers to an enzyme, or OH minus, or to a substrate, I'm sorry, or OH minus transfers to a substrate that causes some reaction to happen, or I should say that speeds up a reaction, and then that H plus is kind of thrown out at the end, okay? And finally, metal ion catalysis. So metal ions are some of the weird ones. Usually you'll see something like zinc or magnesium or iron. Metal atoms are usually cations. Okay, and so they're cation just because I'm sure you guys remember back in general chemistry, we see zinc 2+, we see iron 2 or 3+, we see magnesium 2+, things like that. Having that positive charge, and it's an entire positive charge, it's not a partial charge like a lot of what we see in our body, but it helps stabilize charges that can be formed in a reaction. So the reason this transition state might be so unstable is because maybe it has a really strong negative charge. So having something like zinc right next to it helps stabilize that charge and helps speed up that reaction. Okay, so those are the 4 big types. So we're going to do 1 or 2 quick examples, and these are similar to questions I've seen in prior exams. So what amino acid would you likely find in the active site of an enzyme participating in general acid-base catalysis? What do you guys think? Let's see. B, you're exactly right. Histidine is one of the commons because it's a basic amino acid. A couple of the other common ones are glutamate and aspartate, because those are pretty strong acidic amino acids. They can also really help with general acid-base catalysis. Okay. All right, the next one. And these, I think this is kind of the start of my, oh no, this isn't a review. This is something that was briefly mentioned in this chapter, but it's not really talked about. But I think it ties back more to what we talked about in week 4. So trypsin cleaves to the carbonyl side of either arginine or lysine. But in that peptide, we only see 2 fragments, despite seeing arginine, arginine, lysine. So I would expect to see, I think this should be 3 fragments instead of 4, I apologize. So why does it not cleave as much as it should? There it is, E. Okay, you're exactly right, and that's kind of something to keep in mind. So proline is the really, really weird amino acid, right? It's the one where the N-terminus, central carbon N-terminus, your N-terminus folds in and is part of your R group. So because of that, any bond that has, and keeping in mind your N-terminus, so this is the carbonyl side of your prior amino acid. So if you had an arginine or a lysine here, then this is a really awkward bond to cleave, okay? So trypsin specifically, as mentioned, I think there might be a few other exceptions, or a few other protein, or I should say cleavages that don't, or that can't do what they do because of proline's presence, but I'm not 100% sure. Okay. Does anyone have any questions about trypsin cleavage? Okay. Oh. Okay, awesome. All right, so the catalytic triad of a serine protease. So I asked this question more as a chance to talk about this because I think a lot of people ignore it. So does anyone know the answer to this question before we start talking about it? Oh my God, you're gonna go fast. It is D, and I want to talk about that catalytic triad a little bit specifically. So, okay, there we go. So what is the role of each part of this triad? Okay, so first, excuse me, we see, excuse me, sorry, let me get a drink of water. I apologize. Okay. So we generally will see an acid that orients the base, okay? Then a base to polarize the nucleophile, and a nucleophile to attack the substrate. So the reason aspartate is here is so that the aspartic acid form of it can make histidine a base. The reason histidine is here so that histidine can, as a base, abstract a hydrogen from serine. So serine can have that O- and be a strong nucleophile, and it can use itself being a strong nucleophile to catalyze whatever reaction it needs to catalyze. Okay, and catalytic triads are fairly common. They're not in every enzyme or anything like that, but they tend to come up a lot, especially when we're dealing with those. Actually, ask you guys this: which of these four? So I'm going to go ahead and cross out ionic catalysis. Which of these four types of catalysis would we most likely see a catalytic triad in? Acid base. Okay. Anyone else have any ideas? Proximity. Okay. Covalent. Okay. We're seeing a lot of ideas. So let's talk about it. So and I'm going to use a carbonyl just for convenience. So if this serine is a strong nucleophile, it can attack. Let me just try that again. I apologize for that poor drawing. It can attack that carbon. One more time. That carbon right there, and pop that up. Right. What kind of bond is being made between my serine and my substrate? What do you guys think? It's a covalent bond, exactly. So these catalytic triads tend to appear more often in covalent catalysis mechanisms, simply because when a nucleophile attacks the substrate, it tends to be able to react. Or when a nucleophile attacks the substrate, it forms a covalent bond. Excuse me. So that is most of the kind of big things in the past week's lectures. I wanted to do a brief review of some of the stuff that we've been talking about, the bigger topics, simply because I think that they're, let's see. So the role of aspartate is the acid so aspartate is, I should say, aspartic acid, if we remember, has a pKa around 4, whereas histidine has a pKa, and I should say ASP versus histidine has a pKa around like 6. And so you can see histidine in its acidic or basic form, or I should say in its charged or uncharged form. When you have aspartate is really freely able to give away a hydrogen because it's so acidic. So aspartate is there to make sure histidine is in its basic form. And so once it's able to do that, it takes away serine's hydrogen, and I think they call it polarizes. Sorry, let me make sure I get the official word because it's strange. So yeah, so the acid orients and stabilizes the base, and then the base polarizes the nucleophile. Oh, I'm sorry, I explained that backwards. So the aspartate donates its proton to histidine. Histidine wait, nope, backwards. Yes, histidine is the acid, or aspartate is the acid, histidine is the base. Yes, you have it right. I apologize. I keep going backwards. Yeah. Okay. That is most of the major topics for these chapters. I skipped a couple of like pH dependence simply because we talk about them. I didn't talk much about low barrier hydrogen bonds, partly because they're just really weird. The general idea behind them is that the hydrogen bond, it's a very strong type of hydrogen bonding where, oh, hang on, that is not what I'm looking for. Let me clear this. Basically, your hydrogen bond is almost interchangeable between the two oxygens or whatever it is we're dealing with. And this can be used by enzymes to make sure that everything is stabilized. But that's really like, I don't want to call it a minor topic, but it's not something that I think is really asked about often. So does anyone have any questions about the chapter or two chapters that we talked about this week before I move into some review for the exam? Okay, all right, so I had a couple of questions that I think are most common when we tend to deal with these kinds of, this chapter, or these chapters, I should say, with this unit. We can go through them, and then I have some time. I made sure to leave plenty of time, so if any of you guys have questions, you can ask them. Okay, so we're starting with Esi Mass Spectroscopy, or spectrometry, excuse me. So when we have Esi Mass Spec, and we're assuming that these are neighboring peaks, by the way. I think I made the same mistake before. Neighboring peaks. Okay. How do we set up this this question? Like, how do we solve for what we're trying to solve for? Okay, so x is 912.3. And I think you're referring to the x that's like m plus z over z, right? That's usually what it is. I just want to make sure because I've seen a couple of variations. Yep, okay, perfect. You're exactly right. Y is going to be m plus z plus 1 over z plus 1, and it equals 842.7. So we can solve this algebraically, set up the system of equations, solve both for m, set them equal to each other to get z. Does anyone remember the easier formula? When can you use 1 over z? What do you, sorry, Carol, can you clarify what you mean by that? I don't know that I fully know what you mean. The isotropic peak. Oh, I haven't talked about that specific thing in a very long time. Oh, yes. 1 over z is the distance you have them apart. So if you, I've never used that method before. I'm going to be honest. I don't remember using it much. Generally speaking, you can use this system of equations, but the easier way to do it is, what's it called? It's y, anyone remember x minus y at the bottom? Who remembers the top? Y minus 1, there we go. Didn't want to give it all away. And that equals z. So that's just the quick and easy way to do it. It's okay, to be honest, the isotropic stuff is just super, I don't like it. So y is 842.7 minus 1 over 912.3 minus 842.7. Okay. Okay. So plug all that into our calculator, blah, blah, blah. The number we're going to get out of it is going to be 12.09. Is 12.09 the answer to this question? No, perfect, exactly right. So generally speaking, when we're talking about charges, we mean protons. So 12.09, we're going to go ahead and say it's plus 12, okay? And then the mass, very briefly, what we do is we just say, I'm going to pick this one since the formula is a little easier. I'm going to say 912.3 is equal to m plus 12 over 12. I apologize, that's a bad m. And plugging that in, we get 10 kilodalton. And yeah, we can go into a little bit more specifics, but 10.9 is effectively it. So this is just kind of a reminder, mass spec is here, kind of sucks, but it's a process we gotta do, okay? How long is an alpha helix with 5 turns? So this is just a quick recap, secondary structure. So who remembers the numbers we're gonna use for an alpha helix? .6 what? 5.4 and 3.6, give me a little bit more. 3.6 residues per turn. Is that what I'm supposed to write? Yeah, good, okay. 3.6 amino acids per turn, okay. And then 5.4 angstroms per turn, right? And perfect, exactly right. So we're gonna say 5 turns times, well, let's see. I don't actually care about how many amino acids, do I? So I can just take that 5.4. 5.4 angstroms. And when I do that, I get 27. So my answer is B. Yes? Excellent. Whoever said, yeah, you said C, you're exactly right. Keep your units in mind. This is a very, very common way they like to trick you. Keep in mind, there's my mouse, 10 angstroms is equal to 1 nanometer. So we had 27 angstroms here, and I left off the units intentionally to make sure you guys were paying attention. 27 angstroms is actually 2.7 nanometers. Very good. Okay. Next, Menton. So we have this K1, this K negative 1, this K2, and we want to know at what S is initial velocity equal to 1/2 Vmax. So what are we looking for? Like, what is this asking us about? So you can just find Kn. Perfect. Exactly right. And if you weren't sure, like if you were kind of confused, you can always just say, okay, let's go to V equals Vmax times S over Km plus S. You can divide Vmax from both sides and say V over Vmax equals 1/2, which equals substrate times Km plus S. And then you can solve to get, okay, when substrate concentration equals Km, that's when we're dealing with this initial velocity equals 1/2 Vmax. And then we know that Km equals, say, K1, K2, K negative 1. What do you think? K negative 1 plus K2, and I'm going to go ahead and finish, divided by K1. Perfect. K1. And let's see. Actually, while I'm plugging this all in and writing it out, can one of you guys tell me, are we dealing with a rapid equilibrium or steady state equilibrium? And why? Sorry, I will see your message in 1 minute, whoever just said that. Okay, so that's what we're dealing with. Okay, and the number I get out of this is 6.93 times 10 to the negative fourth. 3 times 10 to the negative fourth molar. Okay, and okay, kind of on topic with rapid equilibrium. Okay, sure. So someone said rapid, you're exactly right. And the reason that we have rapid equilibrium is because K-1 is significantly greater than K2. So the question that was asked, how much bigger does K-1 need to be? Generally speaking, my threshold is about 3 orders of magnitude. And the reason is the I don't want to call it a better definition, but the other definition for rapid equilibrium is when Ks equals Km. So, and I pulled this question from an old review, so I actually want to pull up that review. I think it was week 5. It was week 6, maybe. Yeah, it was week 6. So, yeah, so I got this question, and then the very next, from the previous mechanism, Menton enzyme kinetics following is true, and that's steady state or rapid. When we look here, we calculated Ks and got 6.92 times 10 to the negative fourth compared to 6.93 times 10 to the negative fourth. So I think 3 orders of magnitude is a very safe number. Like if it's above, if it's 2 orders of magnitude, it's probably going to affect Ks and Km a little bit. If it's less, I think you're good. So 3 orders of magnitude is about my threshold, okay? Okay, awesome. All right. What type of inhibitor is present in, let's get rid of that, in this Lineweaver-Burke plot? Non-competitive, I see. Okay, does anyone agree, disagree, not sure? Okay, so let's go through this. So this is my initial V, 1 over V. This is my new 1 over V. So because the Y is going up, I know that my Vmax is going down. My Km stays the same. So what does that tell me? It tells me that my affinity for my substrate is not changing. So, and I go to the formula because the formula helps me think about this. If I if I decrease enzyme because of competitive inhibitor, then I would see a Km increase. If I decreased enzyme substrate concentration, I would see a Km decrease because I have more affinity so that I can get more ES. So what I'm seeing is no difference. In other words, I'm lowering both at the same time. And so that's what makes this, exactly like you thought, a non-competitive inhibitor. Competitive inhibitor. Okay, you're exactly right. Does that make sense? Are we all okay with that? Okay, terrific. I just have one more question for this review, and it's, oh, oops, I forgot that I made a multiple choice. There we go. And it is, does anyone have any questions? Okay, I wanted to make sure to leave some time because I know this exam is kind of a heavy one. So I wanted to make sure that I had time to address any questions you guys have. What do you guys think? If you want to talk about those inhibitors, I skip we can, if that's something your professors want, your professor's covering. If you want to talk about anything from this unit at all, secondary structures, anything. Percentage of beta strand. I think I know what you're talking about, but I don't, let me see if I know the way that it's set up. So the percentage of beta strand, or I guess the percentage really in general, comes down to the fact that you're you're never going to have a super smooth, excuse me, You're never going to have this perfect protein that's all secondary structure, right? When we think about, for example, I have one beta strand, and then to get to my other beta strand, I have to loop around. And so this segment right here is very rarely in a secondary structure. So there definitely is percentage beta strand stuff. I unfortunately don't remember the math problem. If you can find an example, I'd love to work one with you guys. I just don't know where it would be. How much do we need to know as far as enzyme mechanisms? Oh, okay. So I'm going to answer this question, then we can do that example, okay? So enzyme mechanisms, this is another kind of somewhat dependent, but I would mostly focus on knowing each in general so that you can tell them apart. The other thing is if your professor spent like 2 slides talking about serine proteases, those are probably going to, like, I would know those, and that's kind of why I covered them specifically, because they have like 3 or 4 slides dedicated to them in both PowerPoints. Or I should say serine proteases and catalytic triads. So I focus on them because they're common. But so I would, generally speaking, know the big 4. So proximity, covalent, acid base, and hang on, I don't remember the 4th. Metal ion, there you go. I would generally know a little bit about each, like why they work. So like I said, metal ion, metals tend to have positive charges that are like +2, +3. That really helps stabilize a negative charge. I would kind of just generally understand why they help. With proximity, you tend to have questions, or like you tend to be asked things about like near attack complexes. I don't think you should need to know the percentage, or I'm sorry, the angle and the distance. Those specifics probably aren't the most important thing in the world, okay? Right. Yeah, okay, sure. We'll do that right after the example for the percentage beta strand. So if you can paste that question in, I would love to go over, and then we can backtrack to the enzyme classes. Okay, so, okay. So the way that I would approach this is, first of all, I know 15% of its mass is in 64 strands. Okay, that's fine. So, okay. Actually, the first thing that I would do is I see that this is a homotetramer, excuse me. And it's asking per length per subunit. So I'm going to figure out what is the mass of a single subunit. So I'm going to say 102,800 divide 4. Okay, are we okay with that? Homo tells me they're all the same. Tetra means there's 4 of them. So the number I get out of that is the mass of each subunit is 257. Oh wait, I'm sorry, 25,700. Excuse me. There we go. Now I know that 57% of that is going to be in a beta strand. So I'm going to multiply by 0.57. And I get 146.4 in Daltons. Okay. I know that the average mass of an amino acid residue could be 120, but we really use 110. Why do we use 110? Loss of water is why we don't use 138 or 188. But why do I use 110 over 120? I mean, you're right, but sorry, and I keep changing units. So sure, it's a common question. So 120 Daltons is the average mass if I took 1 tryptophan, 1 alanine, 1 glycine, 1 valine, one of every single amino acid, got the mass, subtracted 18 from each of them, averaged them up, I'd get to 120. But what we see in real life is tryptophan is not abundant. Tyrosine, phenylalanine, not abundant. And those are kind of like the bigger ones. So the average that we end up using is 110 Dalton, just because this is of the smaller amino acids that are more abundant. Okay, so I'm going to take my 14,649 and divide by 110. And from there, I get about 132, or I'm sorry, 133 amino acid residues. All right, next it tells me antiparallel beta strands. What is the length of an antiparallel beta strand? Is it the 0.65 or the 0.65? Anybody? Oh, that's okay. It's something you should know for your exam, though, so it's good that we're doing this. It's 0.65 per 2 amino acids, or per 2 residues, I should say. So I'm going to, okay. So the number I get out of this is 43.3 nanometers. Oh, and this is 0.65 nanometers or 6.5 angstroms. Let me, I want to make sure that's clear because sometimes I do forget to mention the units. Okay, so the number I got is 43. I'm willing to say 42 is just they rounded differently than I did, or maybe I should have rounded earlier or something like that. But that's kind of where that idea comes from. Does that make sense? Okay, awesome. Yeah. So I'm going to go ahead and is 0.65 per 2? Yeah, so that's the anti-parallel. 0.695 is for parallel. And the reason that they're different is because the anti-parallel are more stable. I should say they're more stable in the sense that, like, you can put them together and they're a more favorable interaction. Okay. And that dividing by 5.4 is a really, really common thing a lot of people do, is they don't keep track. Alpha helix, beta sheet, parallel or anti-parallel beta sheet. It's something a lot of students get confused or just forget about. So yeah, it's good to make that mistake here so you don't do it on the exam. So I'm going to go ahead and stop sharing this so that we can go back to talk about those enzyme classes. Okay. Okay. So I believe we talked about that in week 5. Nope, maybe week 3, maybe week 6. Yeah, it was at the very beginning of week 6. Okay. So these are the big 6. And so generally speaking, they're fairly different with the exception of lyases, ligases, and in my opinion, hydrolases. So these 3 I think are the big different ones. So oxido reductases, I think tend to be fairly intuitive. See electron transfer, change in oxidation state, whatever it may be. This also includes breaking disulfide bonds. And that's something a lot of people forget, is that could be catalyzed by an oxido reductase. But generally speaking, I don't know if you want me to spend too much time on this one. You specifically mentioned lyases and ligases, because those are the confusing ones, I think. But so I just want to double check. Okay. Yeah. So an actual example is going to be a little bit tougher to come up with one. Give me a sec. Actually, yeah, breaking disulfide bonds is probably the weirdest example you'll see, so I think that's pretty. A transferase could be something like, if I have a methionine, or something that resembles methionine, I should say. So CH2 sulfur CH3, I could transfer this methyl group. So if I have let's say a methyltransferase, I could transfer this methyl group to whatever other protein I have or whatever other structure. And this is actually a fairly common transferase thing that you'll see in Biochem 2 if you guys take it. Okay. Hydrolases are, in my opinion, the easiest way to think about this is formation of a peptide bond. And I want to point out the formation of a peptide bond is actually, it actually uses a ligase because it involves ATP, but peptidases, or I should say, with the exception of making amino acids into proteins, generally speaking, your peptide bond formation is an example of a hydrolase because, and actually this is a fairly common trend. If you have something that resembles an N terminus and a C terminus, hydrolase hydrogen is very common to be released. Okay. All right, now let's get into the weirder ones. Lyases, isomerases, and ligases. So a lyase is just A plus B equals AB. Okay, so this would be something like, gosh, I'm trying to think of a good example. Have you guys learned, or I should say, I think you guys have learned glycolysis, but in glycolysis, if we treat every reaction as being reversible, there's dihydroxyacetone phosphate, and I think it's glyceraldehyde 3-phosphate. You have something up here that splits into both of these, right? I don't remember what it is up there, unfortunately. It might be fructose or something. Well, a lyase is either going to cleave into these two or bring these two back if this reaction doesn't use ATP. Okay. Finally, or I should say next, isomerases would be if I have CH2, oh, actually delete the 2 because I don't want it. Okay. CH, and then I have CH on this side, and then a methyl. And then on this one, I have a phosphate group. An isomerase could, oh, actually, no, that's not a good example. If I delete this hydrogen and add maybe, I don't know, an OH. So a transferase, or I should say, I'm sorry, an isomerase, not a transferase. Isomerase does exactly what a transferase does, but across the same protein. So maybe I will move this CH3 to the OH. Or maybe I will move this PO4 to this OH right here and leave an OH on this side, something like that. Finally, ligases cleave using ATP. So it's a good example of this that you guys probably know. This is a hard one. I'm sorry, I can't think of a good example of a ligase off the top of my head. Let me look one up. Exactly, yeah. A ligase uses ATP. I think that's kind of what it really wants from there. Lyases, do they form a double bond? I don't think they had to, but they might. They can, yeah. A lyase in the equation. Wait, what? Am I on the wrong? Oh, yes, you're right. It tends to form a double bond. And the reason is when I ran out of space. Okay, so I'll draw over to the left side. When you cleave, for example, a carbon-carbon bond, you need a double bond to stabilize the charges. Yeah, so generally speaking, double bonds are pretty common there. They can also fold into a ring as a result of a lyase. Doesn't necessarily have to be a double bond because a ring will also stabilize that charge. Okay? Or I should say some closed conformation, not only a ring, those 3D structures also work. Okay. I hope that answered those questions. If y'all have any more, please let me know. Okay. All right. Well, good luck on your exams. If you have any questions between now and then, we have drop-in tutoring. We have, I think, Biochem tutors most of today and tomorrow. So yeah, feel free to join us and ask any questions you have. I'm going to go ahead and stop the recording.